Let's talk about a quiet but fundamental assumption in modern AI inference, that identical weights, identical prompts, and identical random seeds guarantee identical outputs. In practice, that's not always true. Even when you lock down decoding parameters and freeze the model graph, you can still get behavioral divergence. And in sparse mixture-of-experts architectures, that divergence often doesn't come from randomness. It comes from floating-point arithmetic, reduction order, and accumulator precision. Today, we're breaking down a recent study that traces exactly how numerical state propagates through sparse MoE inference, why reduction order isn't just a low-level kernel detail, and how it can silently reshape a model's execution semantics. To understand why this happens, we need to look at how MoE routing actually aggregates. When a token is routed to a subset of experts, each expert produces an output that gets multiplied by a gate weight. Mathematically, summing those gate-weighted terms is commutative and associative. But in finite precision floating point, neither property holds. Different reduction orders change when rounding occurs, which changes the accumulated value. In a static feed-forward network, a tiny numerical shift might never cross a decision boundary. But in a dynamic MoE decoder, it's a different story. That perturbed hidden state gets consumed by later routers. If the numerical difference pushes a router score across a top K margin, the selected expert subgraph changes. That altered state then flows into the attention mechanism, updates the layer-wise persistent state, and eventually feeds into autoregressive greedy decoding. A small logic difference can flip the next token, which then seeds a completely different trajectory. The reduction order of an expert aggregation isn't just an implementation detail anymore. It becomes a hidden part of the model's execution semantics. To isolate this effect, the researchers ran a controlled intervention on DeepSeek v4 Flash using a native runtime that allowed direct instrumentation of expert aggregation, routing, and persistent decode state. They froze everything at a specific MoE layer. The prompt prefix, token position, selected expert IDs, gate values, the 6 weighted expert terms, the shared expert output, and the full persistent state. The only variable they changed was the permutation or aggregation scheme at that single layer. They tested 4 distinct aggregation schemes that deliberately separate operand representation from accumulator precision. Scheme P32 uses full FP32 expert terms and FP32 accumulation. Scheme C rounds each term to BF16 first, then promotes it exactly to FP32 for accumulation. Scheme A uses FP32 terms, but rounds to BF16 after every addition. And Scheme B rounds both the terms to BF16 and the accumulator to BF16 after every step. Crucially, the runtime implements BF16 rounding in software using a specific bit-level bias rule, ensuring deterministic behavior across runs. For Scheme A, they enumerated all 720 possible cross-expert reduction orders. For Scheme B, they identified 360 exact structural equivalence classes due to a BF16 addition symmetry. The results showed something striking. Despite hundreds of numerically distinct internal states, the divergence compresses into a surprisingly small set of continuation basins. Under a single prompt, different reduction orders produced distinct routing selections and eventually delayed token divergence. Identical emitted tokens early in the sequence did not imply identical autoregressive execution states. Even more compelling was the semantic bifurcation. Under one controlled Chinese prompt, the reduced structural classes split into completely different event directions. Some continuations explicitly described workforce layoffs, while others described hiring. This wasn't random noise. Deterministic replay confirmed that each branch reproduced exactly across multiple runs. The divergence was structural, deterministic, and highly sensitive to the numerical contract at the expert aggregation boundary. Now here's where the state boundaries become critical. The study validated 2 distinct checkpoints for reproducing this divergence. First, the post-mHC state within a single forward pass. By capturing the exact FP32 additive delta between the native reference and a divergent branch, and injecting it back at the same layer, they perfectly reconstructed the downstream intratoken trajectory. All subsequent post-mHC vectors, router selections, and generated tokens matched bitwise. Second, they tested the full persistent state at a decode boundary. This includes the window KV cache, active compressed KV, compressor state, and indexer state, totaling nearly 6 million FP32 values across all layers. A literal FP32 delta reconstruction failed to recover the target bitwise due to precision loss during subtraction. But by computing the delta in FP64, adding an FP64, and casting back to FP32, they achieved exact bitwise reconstruction. When they injected this persistent state delta and let the model continue generating under the same naturally selected next token, all 301 subsequent post-mHC states, persistent checkpoints, routing decisions, and generated texts agreed exactly over 7 decode steps. This proves that numerical divergence can survive a token boundary and become visible later. The post-mHC state acts as a precise intratoken conformance boundary, while the full persistent state serves as a practical cross-token continuation boundary. So what does this mean for the field? It means that backend qualification can't stop at final token agreement. If you're migrating models across hardware, compilers, or runtime frameworks, numerical compatibility must be treated as a hierarchical state transition contract. A practical conformance procedure would start with decode boundary persistent state fingerprints. If those diverge, you bisect the difference across KV components and layers, then enable layer-indexed post-mHC tracing to localize the first observed state divergence. Eventually, you'll pinpoint the exact operator or numerical contract causing the drift. For hardware and runtime designers, the implication is clear. Cross-expert operand representation, accumulator precision, and merge ordering must be explicitly specified. If your combine unit accumulates in arrival order with low-precision sequential rounding, completion order becomes reduction order. That's a semantic shift, not just a performance optimization. Stabilizing this requires either BF16 expert compute paired with an FP32 or guard-bit cross-expert accumulator, a fixed partial sum reduction tree, or deterministic merge semantics. This research doesn't claim that all numerical divergences behave identically across every architecture, or that these exact frequencies will appear on production GPUs. It isolates a controlled causal possibility and proves that reduction semantics are a measurable part of execution. As MoE models continue to scale, treating floating-point aggregation as a deterministic execution contract rather than a replaceable kernel detail will be essential for reliable, reproducible inference. Understanding these boundaries isn't just about fixing bugs. It's about recognizing that in modern AI systems, numerical precision, reduction topology, and state persistence are deeply intertwined. And as we push toward more complex routing and longer context windows, that interplay will only become more critical. If you're working on inference runtimes, compiler backends, or MoE architectures, this is a foundational piece of the conformance puzzle.